Hello all, in this video we will see how to add a noiseless resistor to a given circuit. So let us see what is this noiseless resistors and what do you mean by it. For example, let us form a simple um, op-amp based circuit. Okay, so let us take a universal op-amp. Okay, and then let us try to give some voltage. We are giving some voltage which basically is AC voltage. Let us assume we give an amplitude of 1 for example. Okay, let us try to pull this up. Okay, and then we are grounding this. Okay, and then let us add feedback resistors here. I am adding a feedback resistor of 1k here. Okay, and we are naming this output node as Vout for convenience. Okay, and then again the resistor on the non-inverting terminal. For suppose we have this as 470 ohms. Okay, so a simple op-amp configuration, right? So now let us try to simulate this. For suppose one. Okay, now we don't want to do transient analysis, we want to do noise analysis because we want to see how a noiseless resistor can be added, right? For example, let us try to add noise simulation into it. So output, you can see here the output actually has a V of V out. So during performing noise analysis, we want to perform the noise that is present on the output node. For this, we have to give this way, and then the input is V1. Okay, and then let us take 500 and let us try to start from 50 and till 500 meg. Okay, so this is the simulation command. Now, when we try to simulate, you see an unknown subcircuit. So what we have to do is we have to include op-amp based subcircuit here. We have a video on why to include this. So this is op-amp. You can see OP-AMP. So the same thing has been included. Now, when we try to simulate this, you can see the output, the noise on this node voltage V out is directly given here as 7 nanovolts per square root of hertz. What is actually nanovolt per square root hertz mean? So this actually is nothing but the power spectral density, the noise spectral density. What do you mean by this? This is nothing but for a given bandwidth, the amount of noise power present is indicated by the noise power spectral density. Okay, now the output is seen as this much noise, and then this noise could be thermal noise, right? And this is contributed by all the components in this specific circuit. Now we might want to eliminate noise from some of the circuits. Let us assume we have a ideal components. Now we were talking about how to include noiseless resistors, right? So for this, right click on a resistor and at the value you put it as noiseless. Okay, now let us try to run this. Previously it was 7 nanovolts per square root of hertz, right? Now if you run this, you can see the noise got reduced. Now it is 6 nanovolts per square root of hertz. So as the noise from resistor is not included, you can see the value got reduced. Now as an example, let us try to add a noiseless resistor R2 as well. Now when you simulate, you can see it has gone down to 4 FV per square root of hertz. Wow, it has gone down further below nanovolts, right? Now, just to check, let us try to eliminate the noiseless resistor on the feedback, and you can see it got increased 4 nanovolts per square root of hertz. So, what we are actually saying here is as various elements of the circuit contribute to the output voltage, we can eliminate specific resistors from this particular scenario, the noise contribution by these resistors, and calculate how much noise is being present on the output. So this is how we add a noiseless resistor to a given circuit such that the noise contribution from that particular component is not considered in the simulation.